All right, welcome to The Explainer. Today we're diving into one of the most fundamental, kind of invisible pieces of tech that makes the internet, well, work. Load balancing.
So, let's set the stage. Imagine you've built this absolutely brilliant algorithm on your computer. It's a game changer. You put it out there and it just explodes. It goes viral. Everyone wants to use it. That's the dream, right? Well, yeah, but it's also the beginning of a huge technical headache. Let's walk through what happens next.
So, the first big question is, how do you take this piece of code sitting on your laptop and turn it into a real, actual service that people all over the world can use 24/7?
Well, the first thing you do is create something called an API, an application programming interface. The easiest way to think about it is like a menu for your code. It tells other programs exactly how to ask for something. We call that a request, so your algorithm can do its thing and send back the result, which we call a response.
And just like that, boom, your computer is now officially a server. But let's be real, you can't run a global service from your bedroom. I mean, what if someone trips over the power cord? So you move it to the cloud. You're basically renting a slice of a super powerful, professionally managed computer in a massive data center.
Okay, so this is where the real fun begins. Your service is a massive hit. But that success, that popularity, it comes with a price. Your biggest strength is about to become your biggest weakness.
All of a sudden, we're not talking about a few requests here and there. We're talking thousands, every single second. And that powerful cloud server you're renting, it just can't keep up. It's starting to drop connections, things are slowing down, it's totally overwhelmed.
To fix this, we need to talk about one of the most important concepts in all of system design: scalability. It's a simple idea, really. It's just about how you build your system so it can handle more and more work by, you guessed it, adding more resources.
Now, when you need to scale to handle this flood of new users, you basically have two options. You can either grow up or you can grow out.
Scaling up, or vertical scaling, is pretty straightforward. You just buy a bigger, faster, more powerful server, like a total monster of a machine. Scaling out, or horizontal scaling, is different. Instead of one giant machine, you just buy a whole bunch more of the same machines you're already using.
And this is where you really see the trade-offs. Scaling up is fast, for sure, but you're limited by physics. There's only so big a single computer can get. And worse, it's a single point of failure. If that one supercomputer goes down, your whole service is offline. Done. Horizontal scaling, though, that's resilient. If one server fails, who cares? The others just pick up the slack. And you can just keep adding more and more servers pretty much forever.
So you can probably see why, for any truly massive service, scaling out is really the only path forward. But, and this is a big but, it introduces a whole new kind of problem.
Because now, you don't just have one server, you have a whole fleet of them, an army of computers all ready and waiting to do some work.
So think about it. A user sends a request. You've got, 100 servers sitting there? Which one gets the job? How on earth do you decide where to send it?
This, my friends, is exactly the job of a load balancer. It's like the air traffic controller for your entire system. It's a dedicated piece of hardware or software that sits out front and intelligently directs all that incoming traffic. The goal here is pretty simple. You want to take all that incoming work, the load, and spread it out as evenly as you can across all your servers. You just don't want one server getting totally buried in requests while the others are just sitting around doing nothing.
So how does it actually do that, thousands of times a second? Well, one of the most common ways to start is with a surprisingly simple math trick. So here's how it works. You grab some unique info from the requests, like a user ID. You feed it into what's called a hash function, which basically just turns that ID into a consistent, unique number. Then you use a math operation called modulo. If you have 4 servers, you just take that number, divide it by 4, and look at the remainder. The remainder is always going to be 0, 1, 2, or 3, which points you to the exact server to use. Simple. And for a while, it works perfectly.
But then, it happens again. Your success is unstoppable. The traffic just keeps growing, and now 4 servers aren't enough. You have to add a 5th one to the fleet.
And this is where our nice, simple math trick just completely falls apart. The instant you go from 4 servers to 5, your equation changes. You're not dividing by 4 anymore, you're dividing by 5. And that one little change causes a catastrophic chain reaction. The result of that equation is now different for almost every single user.
You get what's called a mass reshuffle. A user who was always sent to server 2 is now suddenly sent to server 4, and someone from server 0 is now on server 1. Now, this might not sound like a huge deal, but it has a disastrous side effect, and it all comes down to caching.
See, to make things feel fast, servers keep a user's data close by in their own memory. That's a cache. But when that user gets reshuffled to a new server, all their cache data is back on the old machine, completely useless. So the new server has to get everything from scratch from the main, much slower database. And for your users, the whole app just starts to feel slow. It grinds to a halt.
The impact is just brutal. We call this a cache miss. The server goes to look for the data it needs, and it's just not there. Think about that for a second. The very act of adding a server to make things faster has actually made almost every single request slower. It's the exact opposite of what you wanted.
It's really kind of ironic, isn't it? You scaled out to handle more load, but this simple, kind of naive approach to load balancing just made your entire system slower. All that useful, time-saving info in the cache, it's gone. Useless. And this leaves us with a really fascinating engineering problem. How do you design a system that can grow on the fly without getting total amnesia every time you add a new machine? That's the challenge that leads to much smarter solutions, and we'll explore those next time. Thanks for joining me for this explainer.